Bon dia, buenos días, good morning. Benvinguts a la Salle, benvinguts a la Universitat Ramon Llull. Welcome to la Salle, welcome to the Ramon Llull University. És un plaer poder rebre'ls aquí a la Salle per participar d'aquesta conversa 2 per una nova transformació entre el doctor Vint Cerf, pare d'internet i vicepresident de Google, i Andreu Veà, Digital Champion for Spain at the European Commission. En primer lloc, té la paraula el director general de la Salle, Campus Barcelona, el senyor Josep Martí Santos.
Bé, molt bé. Doncs, com deia el Fèlix, primer, molt bon dia, welcome to la Salle, welcome to Ramon Llull University. Dèiem que és un plaer perquè per molts de nosaltres el senyor Vint Cerf ha estat una persona significant a la nostra vida. Els que hem estudiat enginyeria, els que ens hem dedicat una miqueta a aquest sector, d'alguna manera ens hem vist cridats a tirar endavant projectes perquè aquest home va inventar una sèrie de coses que ens han fet a tots la vida més fàcils. Una d'elles és un dels pares reconeguts d'internet. Mr. Cerf, we would like to express our tremendous gratitude and welcome you to this event because to be here for us is a special day. It's a special day. Thank you also to accept the honoris causa of the Ramon Llull University we'll take tomorrow. You are a mentor, as I mentioned before in Spanish, for many of us. Actually, we find ourselves in the technological present here today only thanks to the advances that you initiated long time ago. Thank you for your vision of the future. We are convinced that these days that you are going to spend with us here in Barcelona will be a great inspiration for everyone here on the campus, for students, for faculty, for researchers, entrepreneurs, and to continue move forward in innovation and technology, which are the pillars of our institution. It will help us to create the new future, as we say in the title of the speech. Thank you very much. Com molts vosaltres ja sabeu, aquí a la Salle fa 50 anys que fem una cosa que va ser novedosa en el seu moment. Van ser pioners en els estudis de telecomunicacions a Catalunya. I aquest any que estem de celebració, aquest 65-66, en 1900, quan van començar els estudis, i no hi havia altres aquí que ho fessin, van celebrar aquest 50è aniversari, aquest curs, amb l'inici amb el Paul Macapetris. Paul Macapetris amb el tema de l'idioma, estic anant a l'anglès tot el matí parlant en anglès, però va ser el fundador del DNS. I avui tenim aquí, durant aquest curs acadèmic, el senyor Vint Cerf, que és el creador del TCP/IP, com dèiem abans. Per què ho fem, això? Per què ens referim a aquestes persones? Doncs perquè ells van ser també dos referents, dos visionaris. Com en el seu moment, nosaltres vam tindre l'oportunitat de crear aquesta facultat que ha donat tan bon fruit i que més endavant va ser pionera també en altres temes. I recordo que va ser la primera, som els fundadors de la primera universitat privada d'Espanya, la Universitat Ramon Llull, estem al 25è aniversari de la creació d'aquesta universitat. Van ser els primers en fer els estudis d'imatge i so a Catalunya, els primers en crear a Europa una enginyeria al voltant de la multimèdia i els videojocs, els primers també, en aquest cas també a Europa, en crear un MBA relacionat directament amb innovació, emprenedoria i gestió tecnològica, primers també en crear la primera universitat privada amb estudis d'arquitectura també a nivell de Catalunya, primers a Europa en crear pioners, per tant, un parc d'innovació dintre del campus, un parc d'innovació tecnològica que crea empresa i que fa emprenedors dintre del propi campus, els primers de gestionar tot aquest coneixement i posar-lo, ara fa un moment en parlàvem amb el doctor Vint Cerf, no només enginyers i persones de negocis que posen junt les idees i fan que siguin possibles. I van fer els primers estudis d'EOTIC a Espanya, una enginyeria i business, i els primers estudis de direcció d'empreses tecnològiques, perquè la tecnologia està canviant el món i la direcció d'empreses s'ha d'enfocar en un nou tipus d'empreses, una empresa on la tecnologia és el driver que fa canviar aquest futur. I la primera, enguany, és el segon curs que fem, de crear animació. No només creem enginyers, sinó que també estem creant el contingut, el que seria el software i els continguts d'internet i efectes visuals. Diem que formem professionals en futur perquè el futur està canviant i està canviant a una velocitat molt i molt gran. Tan gran és aquesta velocitat que de vegades en les xerrades que fem a les noves persones que venen a estudiar aquí a la Salle els diem que els hem de preparar per una cosa que encara no existeix i que treballaran a empreses que encara no existeixen. I això és un gran repte, no? I per això tenim aquest ecosistema on empresa i universitat es donen la mà i creen aquest futur, no? Innoven per crear aquest nou futur. Ciberseguretat, internet de les coses, big data, smart cities, transformació digital, són paraules que ens venen al cap quan estem parlant aquests dies de la transformació, no? Inclús ara estem a la fira de 3D printing, no? Com serà l'arquitectura en un futur amb el 3D printing, com es faran les coses, com canviarà, com es revolucionarà el mercat a partir de tot això. Bueno, aquesta és la clau d'innovació que ens posem ara tots aquí davant. I per això no em vull allargar més i donar-li la paraula tant a l'Andreu com al Vint Cerf i que segurament serà una xerrada superinteressant sobre com veuen aquest futur i com ens poden aportar noves coses, noves idees, innovació a les persones que estem aquí. Només dir-vos que escoltem tot aquest discurs, tota aquesta xerrada i col·loqui formal de forma amb una ment molt oberta, amb moltes ganes d'avançar, perquè està a les nostres mans aquest futur. Thank you, Mr. Cerf. Thank you, Andreu. The stage is yours. Thank you very much.
Thank you so much. I will make a short introduction in Catalan and then we switch. Bon dia a tothom. De fet, estic molt content de tornar a estar a casa, perquè aquesta és la meva escola d'enginyeria, aquí m'he format. Durant 10 anys això va ser la meva primera residència. Aleshores, doncs, estava més hores aquí que a casa. I, d'alguna manera, doncs, estic molt content, m'agradaria saludar-vos un per un, perquè us coneixo quasi tots, les empreses, els innovadors, els enginyers, tots els que esteu aquí. I per mi és, com podeu comprendre, un plaer. És el meu dia, de la meva vida, a vegades que dius que aquestes ocasions és una o ninguna, no? Doncs aquesta vegada de poder presentar-vos al meu bon amic, mentor, mecenes, el doctor Vint Cerf, al qual ara m'agradaria que trenqueu tots els estereotips, posar una conferència més. No, això no és una conferència, això és una cosa que hem dissenyat, fixeu-vos, que hem dit the best way to predict the future is to invent it. No volem predir el futur, volem inventar-lo. El Vint Cerf sempre està 40 anys davant de les persones. Dir, escolta, fa 40 anys va inventar internet. Diem noves tecnologies, potser haurem de canviar-li el nom, perquè molt noves no ho són. Tecnologies sí, però noves 40 anys, d'ARPANET fins ara. La pregunta és, escolteu, doncs imagineu que d'alguna manera ara poguéssim tornar endavant. Ell està, he's working right now in the Interplanetary Network system. So, have you thought about to connect all the planets? Maybe in 40 years this will be useful. Right now, it's, most of us, we didn't even thought about it. So we will talk about these things. Una altra cosa, one other thing that La Salle has authorized me is to change the studies of La Salle according to what we talk about this conversation. And it's not a conversation with him and I, it's only a true conversation with people interested who are business people, who are students, who are most of us. Our community, as you know, La Salle is an incredible well of innovation that is always in front. 50 years ago, there was no telecommunication studies at all. We were there. Right now, the world has changed, and has changed thanks to Professor Vint Cerf, has changed about the internet and all these things that we are connecting to the internet. But most of the humankind, we don't know about that. We keep doing as if it was the same thing. La Salle is here. La Salle, later on, we will see that is creating a new center of Internet of Things devoted to this, putting engineering, building, architecture, business, all together to help this transformation happen in our local community in Catalonia. So maybe what we could make is to try to start up, to warm up, to make like 3 pieces. So we talk a little bit about the past, then we talk about the present, and the most difficult thing will be about the future, of course. So I was telling you that 40 years ago, what were you doing? You would never probably thought that what you were doing UCLA at the time was going to have this impact, is the general impact to the world, right?
Well, you never can know for sure what will happen. If you take on a task and it works, then other people will figure out ways to expand that capability. So when we were starting, this was a project of the Defense Department, and they were interested in, in using computers for command and control. The idea was that if you could use computers to manage your resources, you might be more efficient than someone else, your opposition. And that means you might be able to use a smaller force to overcome a bigger one because you managed it better. We call this a force multiplier. But in those days, we're talking in the 1960s, late 1960s, there were computers that were networked, but they were proprietary networks. IBM had Systems Network Architecture, SNA. Digital Equipment Corporation had DECnet, and Hewlett-Packard had something called DS, which I think stood for Distributed Systems. So the computers of the day could communicate with each other, but they couldn't talk to other brands of computers. So our problem was to allow the Defense Department to purchase any brand of computer then and in the future and make them all communicate with each other, independent of whether they were made by IBM or Digital or HP or anyone else. So we were looking for a non-proprietary way to allow different kinds of computers to communicate. The first attempt to do that was called the ARPANET. It stood for the Advanced Research Projects Agency Network. It introduced for the first time on a large scale a technology called packet switching, which is very different from the telephone system circuit switching. If you know anything about postcards, you know everything you need to know about packets because they behave the same way. When you put a postcard into the post box, there's no guarantee it will come out on the other side. It's called a best effort communication system. If you put two postcards into the post box, destined for the same destination, they don't come out in the same order that you put them in, if they come out at all. So we designed a set of protocols, packet switching protocols, that had exactly those properties. No guarantee of delivery, no guarantee to keep things in order. And the question then was, how do we make this work in a more reliable way? And so we decided to design this in layers, like a cake. And we were very careful to say that the internet layer would not know anything about how the packets were being moved, just like a postcard doesn't know if it was going on an airplane or on a boat or in the car or a bicycle. The postcards don't know and they don't care. The internet packets also don't know what they're carrying, just like a postcard doesn't know what you wrote on it. This turns out to be really important because if you invent a new technology for carrying postcards, you can put it into the internet without changing any of the internet protocol layer. So we brought in optical fibers, for example, satellite communications, all kinds of other technology, including now mobile phones, are part of the internet environment, but the basic packet switching is still the same. If someone invents a new application, you don't have to change the network because the network doesn't know what the bits of the packets mean, like the postcards don't know what you wrote on them. All you have to do is change how the bits are interpreted at the edges of the net. And so when someone wants to offer a new product or a new service, they can put up the computers, write the software, and transmit packets back and forth. The network doesn't change because it doesn't know and doesn't care. So we call this permissionless innovation because you don't have to get permission from all the internet service providers in order to build a new product or a service. And that's why the internet has grown so quickly, why the new applications have come along in such quantity, because no one had to get any permission to invent something new. And that's why Google came out of a dorm room at Stanford. So did Yahoo. Amazon gets built by Jeff Bezos. He doesn't ask permission from anyone to do it. He just puts up the servers. So this is a big lesson to learn. You want people to have the freedom to try their ideas out with as little interference as possible. And that's what we did with the internet design. So when we were starting, we started out with this idea of a non-proprietary architecture. And then we went on to explore new kinds of packet switching with radios, mobile radios in the 1970s, satellite in the 1970s, packetized voice in the 1970s, packetized video in the early 1980s. Not very much capacity, so we couldn't do a lot of it, but we could demonstrate that packet switching could do all of those things. And that's part of the secret of future evolution. Once you show people it's possible, then they can begin to decide, how much more can I do? How do I scale this up? Can I get faster communication? Can I use optical fiber? Can I use lasers? Can I speed things up? Can I get more memory? Can I get more computer capacity so I can do more things? So once you demonstrate it's possible, then you allow for people to accelerate the rate at which you, and the capacity that you have to scale up. And that's what's happened in the internet. When YouTube was first developed, there wasn't enough capacity in the network to carry very much video. Today, 500 hours of video are being uploaded into YouTube per minute. 500 hours per minute are going in. And in terms of how much video is being watched, I don't have a clue. It must be an enormous amount is going out the other way. So this quote over there is really, I stole that from Alan Kay. Alan Kay was the one who said, the best way to predict the future is to invent it. And he was right, because once you show that something can work, then other people will want to figure out how to make more of it happen, or to take advantage of it. So
let's talk a little bit about the origins of the internet. And most of the people know the ARPANET and then goes to the internet directly. But there's the NSFNet, which is I would say the real mother, because maybe the other is the grandma. No? The ARPANET would be the grandma. And also that the NSNet, and there was a public network, the core, and all the NICs and all the
Yes.
network interchanges. And then it happened that was a public network, but then was not privatized, but remember all the Steve Wolf, what happened there, and also it's an interesting and very dark side of the network, because nobody talks about that the moment that
you don't mean dark side in the sense of abusive behavior on the network?
No, in the sense, no, the side of the force.
You mean just not well documented?
Historically, it's not very well documented.
Okay, so this is actually a fairly important lesson in several ways. When we started, we had just the one network, the ARPANET, and it allowed different kinds of computers to interconnect. Bob Kahn and I were thinking about mobile radio and satellite, and we built different networks, a packet satellite net, a packet radio net, to go along with the ARPANET, but they were separate. And we had to design the internet to link them together. We had to design an internet address space, because each of the networks thought they were the only network in the world. And if you said, please send this packet to that other network, you didn't know how to say that. So we had to invent the vocabulary for that, plus the protocols. So we get all of this working, and then for the military, and we demonstrate it. And then around this is still an experiment until 1983. So for 10 years, from 73 to 83, we are running the experiment, changing the protocols, testing to see what works. It takes 10 years to 1983, and we turn it on. And as soon as we turn it on to run, permanently, then the academic community starts to get very interested in this. So the National Science Foundation decides it wants to connect 3,000 universities around the United States. And it also wants to connect networks and universities who are outside the United States. So they start paying for the development of the National Science Foundation network backbone. But they're very smart, and they're thinking, if you're the one running the NSFNet backbone, and you have to talk to 3,000 universities, you'll never be able to do that. So they said, let's build networks in between. So they called them intermediate level networks between the NSFNet backbone and the schools. So we had regional networks, a dozen of them, to serve the universities in different parts of the United States. And then they connected to the core network. Once this started in the mid-1980s, so we start seeing the universities are coming up. Oh, by the way, it didn't hurt that Unix had been invented from AT&T, and Ethernet had been invented from Xerox PARC for local area networks, making it very cheap to connect things together. We also had research things going on at NASA and at the Department of Energy. And so they're collecting information from satellites and from telescopes, and the Department of Energy is running these big high-energy experiments. They also built internet backbones, and we connected them all together. So for 5 years, we're running the NSFNet backbone, the Energy Sciences Network, the NASA Science Internet, plus the ARPANET. And I realized in 1988, after 5 years of operation, that the general public doesn't have access to this. And the question is, how could the general public ever get access to this internet? And I thought, well, the government isn't going to pay for all of our personal use. So we have to build an economic engine under the internet to make it self-sustaining as a business. So I got permission to connect a commercial electronic mail service to the internet, to break the rule that said no commercial traffic on the government backbones. That was a no-no. And so I got permission to put my MCI mail service, which is something I built for MCI, onto the internet as a test, just an experiment to see if we could make the protocols work. Well, as soon as we got this up and running in 1989, 3 commercial internet services popped up. Oh, and the other electronic mail services, the commercial ones, said, wait, how come those people at MCI have this special privilege? We want to get onto the internet too. And so Telemail and OnTime and Geisco and CompuServe all connected themselves to the internet. What they didn't realize is that as soon as they did that, they were matching the standards of the internet for electronic mail. Suddenly, all of the subscribers in those private email services could talk to each other through the internet. The big shock. You mean my client, my customer on CompuServe can talk to the customers at MCI Mail and they don't have to pay? No, they paid you. You got paid, and the MCI people paid, and then they just exchanged mail through the internet. And this is a big shock. This same year, 3 commercial services start up. And so the real beginning of internet's commercial incarnation comes in 1989. And we started tracking how big is the network. It's doubling every year for the next 4 or 5 years. So the thing is taking off. And just about 1993, Tim Berners-Lee's World Wide Web shows up in the general public with what was called Netscape Communications. In 1990, well, actually that's 1994. 1993, the Mosaic browser shows up with graphical. Suddenly the internet looks like a magazine and everybody is excited. So 94 comes Netscape Communications. 95, they go public. The stock goes through the roof, and the dot boom is on. So now we're watching this network grow 100% a year, every year, until April of 2000, and then the dot bust happens. But the network keeps growing. So the dot bust was all about investors throwing money at anything that sounded like internet, stupid. But the basic network service was very valuable, so it kept growing 100% a year for quite a while. So we're seeing what happens when you make something commercially available. So the economic engine is going, the World Wide Web reinforces that, whole new businesses get created around the World Wide Web. And so this was a very explosive period in the internet's history.
Have you ever seen the history of the internet like this? There is like a dark period, which is 1985, 1995, that everybody's talking about the ARPANET, 1960s, blah, 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 1995, the internet. But
what happened in between, right?
Exactly.
Yes.
And why we call him the father of the internet? It's not only because he co-created the TCP IP with Bob Kahn, but he created so many, the Internet Society, then you were at ICANN. In most of the social, I would say, organizations that took care of the internet, he was there. He's like the Forrest Gump. I was there.
So actually, what Andreu is saying here is actually important. The institutions of the internet were created not all at once and not at the beginning, but as they were needed. So an example, when Bob Kahn and I were doing the first work in the 1970s, around 1979, we're both at ARPA, and he says to me, what happens if you get hit by a bus? And all the stuff in your head goes away. He says, we have to make sure that it's in other people's heads. So we started something called the Internet Configuration Control Board. It sounded so boring. We didn't want anyone to join except the people we picked. So I picked the people who were running the research projects that were making the internet happen. That turned into the Internet Architecture Board eventually. And then spinning out of that was the Internet Engineering Task Force, where all of these engineers are inventing new protocols, finding new ways of making the internet happen. And then when the government said, okay, this is now a commercial enterprise, we're not going to support the Internet Engineering Task Force anymore with the Secretariat. You have to go figure out how to fund that. And this is about 1990. And so I'm thinking, well, we have to find a way to get money to support the protocol development. So we invent the Internet Society, and it becomes a nonprofit organization whose members pay dues, and their money is being used now to support the Internet Engineering Task Force standards making. And then comes 1998, and the US government is saying, we've been paying companies we've been paying private sector research institutions to manage the domain name space and the internet address space. We're using government research money to do something that looks like it's really a commercial activity. Why don't we just hand this over to the private sector? So they invent the Internet Corporation for Assigned Names and Numbers. Its job is to hand out domain names and hand out internet addresses and to manage all of that. And so it gets invented in 1998, and I become chairman in 2000. So this is important to know that you can create institutions that are needed when the need arises. You can't know ahead of time exactly what you're going to need until you can see what's happening in the community.
Mm-hmm. Well, so imagine that such an easy way to explain the internet. He had, as he was vice president of MCI, which later became MCI Welcome, he had a private email. He connected it to this core, to this public core of NSFNet, and other companies did the same after that, right? And we are doing this right now. Our organization, our companies, we are connecting to the core, and then we are creating this garden of little gardens connected, and without losing our ability to manage our local network. That's the miracle, no? It's not, if you connect to the internet, you don't need to change your own
That's right.
local network, and that's why the explosion.
The only thing we ask is that you follow the protocols. And when you look at a picture of the internet, there's hundreds of thousands of networks. They're all interconnected to each other. Each of the operators of the network can choose what equipment they want to use. They choose which software they're going to use. They decide who they're going to connect with and on what terms and conditions. It's completely distributed. There's no top-down control at all. It works first because people want it to work. They cooperate with each other. It's like the human towers that we saw yesterday in Villanova. The people have to cooperate to build a tower that's 8 stories high. The internet is like that. You have to cooperate with each other to make it work. And so there's this enlightened self-interest that's driving all of this.
Mm-hmm. Let's talk a little bit about the present. We talked about the past. Let's move forward to the present. And I will say 4 words. It's wine, weight, CO2, and blood pressure. I said, what to do all these things?
Yeah, why are you saying those 4 things?
Yeah, well, the idea here is you're a very wine aficionado, more than
this
aficionado.
is true, yes.
Okay. And then you take a lot of care of your cellar.
This is true.
I'm telling you about the temperature, humidity level,
yes,
right?
This is true.
Well, I don't care much about my weight, but I measure twice per day. Then CO2.
Is this a form of OCD?
OCD?
OCD, yes. If you measure your weight twice a day, that sounds like...
No, not at all, no. It's just a matter of big data. We're talking about big data,
all right, fair enough.
Personal big data, and blood pressure. For instance, my father here in front, he's taking his blood pressure, as many of us or people does, to control the blood pressure. And all this is connected to the internet.
That's true.
700 kilometers away, I know the blood pressure of my father twice a day. I know my weight. You know all your wines from here if they are taken care of. So we are talking about real Internet of Things that matter. The Internet of Things is not, we always put that example that someday our refrigerator will be controlled, you remember that if you don't have milk, then they will tell you, oh, you have to buy milk. That's fine, but that's
not very exciting.
It's not very exciting, but knowing that you have your blood controlled, knowing that your wine is not a good, this is the things that matter.
Well, yes, that's right.
Right?
So
my wine,
I have a couple thousand bottles in the wine cellar. By the way, I'm in the right place for this. Priorato is one of my favorite places for this. And Penedès also, very good. So yes. So I'm monitoring the wine cellar for temperature, humidity, and the levels of light in the cellar. Every 5 minutes, that data is going into a server through a mesh network that's running the IPv6 radio protocols. So this system is self-organizing. And if the temperature goes above 60 degrees Fahrenheit, how much is that centigrade?
How many, you said?
60,
which is,
so it's like 32, 18, 15?
Let's ask some engineer, because without the calculator, I can't make it, but Google it.
There, you
Google
can look it up. It's probably around 15 degrees centigrade. So if it goes above that, my wine is warming up, and I get an alarm message on my mobile that says your wine is getting warmer. So I can remotely reset the cooling system. And that's very important to me with having a big investment in wine. But I also wondered if when I'm away that somebody might take some wine out of the cellar. And I can tell if somebody went in because I can see that they turned the lights off and on. I don't know what they did in there. So I'm now hanging RFID tags on each bottle. And I can do an instantaneous inventory of all the wine in the cellar, and so I can see if some bottle left the cellar without my permission. And I was describing this system to one of my engineering friends, and he says, "Your design has a bug in it." I said, "What do you mean?" He says, "Well, you could go into the cellar and you could drink the wine and leave the bottle there in the cellar."
And that's it.
So now I have to put sensors in the cork. So before, and as long as you do that, you might as well sample the esters to find out, is the wine ready to drink? So before you open the bottle, you interrogate the cork. And if the cork says that the wine got up to 85 degrees, Fahrenheit, that's the wine you give to somebody who doesn't know the difference. So it's very useful to have this capability in the house. And as what you were saying, by extension, says that we will instrument all of our buildings. We will instrument the cars, our homes and offices. We will instrument ourselves over time, partly in order to be warned if something is abnormal, partly to get feedback about how we are using resources. Are we consuming too much electricity? Why is that? Well, you were running the air conditioner during the peak load, and it was more expensive because you had to run power generation that was only needed 2% of the time. All this feedback is telling us in concrete terms how we are using or abusing resources. And I'm hoping the feedback will cause personal change. But it can get more interesting than that, because when the whole city is being monitored this way, now we can start to think about a smart city. And I know here in Barcelona already, you're looking at how to instrument the city to help us understand resource consumption, to deal with congestion of the cars. I mean, this is the beginning of a very interesting evolution in our use of information.
Well, when I say things that matter, I started reducing my gas consumption in the house for 40%.
Wow, that's
I
significant.
will tell you how later. But
You put on a big sweater.
Exactly, exactly. And now it's global warming and the local freezing,
Yes, right, yes.
But that being said, the idea is that just putting some piece of hardware somewhere in the house, or for instance, I've reduced also 20% the electricity consumption, in the power place. You put it there, and it goes and makes a Wi-Fi access point connecting to your mobile, and then you can check every time the refrigerator turns on. The system models each of the devices of the house, and then it starts and it's sorted. Oh, this is the most power
The one that uses the most power, right?
Oh, you go out of the house. You expose or you rechange or replace, or doing only this. You can know what are the hours that you for the first time you have information on what are you doing, and then you can act. You can act. It means, oh, your company, I am going to change my plan. Because I am normally at home at night, no more than that, then I prefer a plan which is more suitable for me. This is 20% of electricity. With gas, 40% of 300 euros per month during the winter season, it's a lot. And it's a recurrent fee. So it's important, things that matter, Internet of Things. Don't think about the Internet of Things, blah, 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 in the smart cities. No, 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 in your house, in your pocket. In Catalonia, this they will understand very well. Okay, it's an important thing. So let's talk. We are talking about the present. This is not the future. You can go to the hardware store and buy this stuff and reduce your power consumption, the gas consumption, even the water consumption. Let's talk a little bit about cyborgs and people like Larry Smart, your friend.
So Larry is an astronomer by trade, but he decided that he wanted to know more about how well or how poorly his body was working. So he instrumented himself. This is called the quantified self. He's probably the most quantified person in the United States. His DNA has been fully sequenced more than once. He is sampling all of the blood pressure and doing analysis of the chemistry of his body, the biochemistry of his body on a regular basis. And he accumulates this information over years. And he has this giant display, which is the size of this entire wall, so he can show all of the information over a period of time. So we can see how these parameters are changing. He noticed that there was a correlation between not feeling well and some of the things he was measuring. He discovered he had something called Crohn's disease, which is about your digestion. And nobody knew this until he noticed the correlation. So he self-diagnosed based on the data he was collecting. So this notion of understanding and monitoring on a regular basis gives you a baseline. And that lets you say, I have departed from the baseline. I've departed from normal. You should check this to find out if there's something wrong. If we were all monitored that way, we might be able to catch diseases and other kinds of problems with our bodies before they get really severe. But we don't have that baseline. Most people, most men anyway, never go into the doctor until they're almost dead. And so the only sample the doctor has of these guys is that you're always sick, because you're never there when you're healthy. So this is not the baseline. So it's the wrong measure. This idea of knowing what's normal turns out to be really important, and monitoring on a continuous basis tells you what's not normal. And that's really important. As you say, things that matter, if you care about your body, that's important.
For instance, when you say you go to the doctor, you say, what's your weight? 73. But 73 when? Because 3 months ago? Because what was the last time you got a weight in a scale? Maybe 2 months ago or 1 week. But in any case, if you take the samples twice per day, you will see it even in the same day, your weight can change 2 kilograms the same day. So taking a sample 3 months ago
exactly.
has nothing to do.
This is called undersampling, right?
Undersampling, that's a word. The Nyquist, no? The Franquist. Here they understand here.
Yes, that's what I like about
exactly.
that.
That's
that's
joke can
great to have engineers around. You can make geek jokes and they laugh, right?
Look at him. And that being said, the idea of not only the weight, the idea of if you are a diabetic, knowing your levels of glucose constantly, it's perfect. Or knowing, for instance, after 47 years of being here at the Earth, I didn't know that in my place, until I took a picture every minute in my window during 3 months, I never noticed that the sun, when the sun sets in 17 pictures, it means 17 minutes goes to the sunset to dark, completely darkness. But then it takes almost 2 hours, 120 pictures, to rise. I never noticed of this imbalance. And this is not only in winter and summer. No, it's always like that.
Do you think someone's messing around with the sun?
I don't know, but nobody told me that when I was a child. You know, the sun, it takes a lot to turn on, but turn off is 17 minutes. This is a joke thing, but it's real. But it's something that you can do after you take a picture every minute. I am telling you, why you take a picture every minute? I don't know, but in this case, it let me know this case.
This is another example of obsessive compulsive disorder.
Exactly. I knew it. Let's talk about your cellar, Vint. Let's talk about your cellar, okay? It's not one by one. But that being said, there's another OTC, as you would say, is taking, you are taking a picture, but I am taking more pictures than you. I'm taking in this small capsule here, which is nothing small, there is no turn on and off button. It's always on. It's taking a picture every 30 seconds. I can program to 20 seconds, but I think 30 is enough. But you will ask me, why do you want that for?
Why do you want a picture every 30 seconds?
Exactly. I knew it. I don't know. I don't know the answer now.
Yes.
I probably in 2 or 3 years, I will tell you. But I will have a big data, a personal big data. I don't publish at all, don't worry. But I will have a huge amount of pictures of what I call my lifetime bits, which is an amazing collection of pictures. I would say it's probably, well, when you are in a meeting and you didn't know if that guy came over or, well, then you, oh yes, he was there. So you make the notes, for instance, of that meeting. Or it's an analysis of all your, it's a time log, but a visual time log. At that time I was there, on the time I was there. And it's not for you, it's from your environment, okay? And you will tell me, what do you want this for? But I cannot answer that. I'm just telling you that I'm doing this for 1 year. I have a big disk drive, okay? And also, here, let's talk about another thing. I said disk drive. Magnetic things that break, something that we cannot access. How many kinds of USB you were telling me the other day? And I introduced you the concept, and this is present. It's not future or past, it's present. Right now, you probably have a lot of pictures, and what I call caca pictures, because this is terrible. This is, it's, what you're doing with this is a mess, because you don't sort it at night. You put it here, this is the concept. No. I still bring a camera, because 1 square millimeter here cannot compete with 4 square centimeters by light.
He's selling these in the back of the room.
Yes,
there.
exactly. And I was selling the thing. And let's talk about one of the problems that you always like, is what are we doing with this? It's nice, but probably our generation will lose, for instance, my grandpa or my great-grandfather. I have really small and few pictures from him, but are really nice. Think about it, about your sons. Not your grandsons, no, your sons or your niece. In 10 years, and I am not telling you in 50 or 100 years as my great-grandfather. I'm just telling you in 10 years, will they be able to watch your pictures?
So this is the looming digital dark age, which I worry about. Some of you may still have 5 1/4 inch floppy disks, or 3 1/2 inch floppy disks, or maybe you have some CD-ROMs, or maybe you have some DVDs, or maybe you have some Blu-rays. Maybe you still have VHS tapes or PAL tapes. I don't know which flavor is used here. The problem with these media is twofold. The first one is sometimes they just fail, like the oxide comes off the tape when you read it and that's it. Or you can't find a piece of equipment that still works that can read the bits in the first place. But let's pretend for a moment that you were clever and you said, well, I know that these media and the readers for them may not work forever, but I know that we keep having these new technologies, optical discs and so on. So I'll copy the bits from one medium to another to make sure that I always have a reader that can still read the bits. It's 10 years from now, and you're reading the bits. And you bring them into an application program, which is running on some computer that you have, which has some operating system on it. And this application software, which is supposed to help you manage your pictures, doesn't know how to render an old TIFF image or a JPEG image, which is from the older formats. It just puts up a big black thing and says, I don't know what this is, it must be a corrupt file. It's not a corrupt file. It's just an uninterpretable file because the software wasn't backward compatible. There's no guarantee that anyone is going to assure you that whatever you create, whether it's a picture or a spreadsheet or a presentation or a text document, there's no guarantee that the files that you created now will still be understandable 10 years from now, or maybe even tomorrow. And so now we have the problem. If we really want to hang on to our history, we're going to have to hang on to the ability to run old software. What if the old software won't run on the new computers? Now we have a problem. I still have the operating system, I still have the application, but I can't feed it into the computer of the future. So one of the solutions to this problem is to learn how to emulate, using virtual machines, old hardware that you can load the old operating systems on, run the old application to interpret the old file. It's not the solution to everything, but it's something we're going to need, as every one of you either has experienced this problem or will experience the problem. Concrete example. I have 1997 PowerPoint files that were created in 1997. I have the 2015 version of Microsoft PowerPoint. When I tried to load the 1997 file, it says, "What's that? It must be a corrupt file. I don't know what it is." And I'm sitting here saying, "It's a PowerPoint file!"
With same company, same application?
Yes, okay. And you know, I don't really blame Microsoft. Backward compatibility, no, seriously. A backward compatibility over 20 years in this business is very unusual. It's very unusual. So I now have an old IBM ThinkPad, which is still running the old software and operating systems, but my good friend Mahadev Satyanarayanan, we call him Satya because nobody can say that whole name. Satya at Carnegie Mellon has built software that will emulate old hardware. So there is a chance, if we set up a regime of preservation, that we can keep the descriptions of the hardware, keep copies of the old operating systems, and copies of the software so we can interpret the old files. And without going into a long dissertation, you need to think a little bit about the legal problems associated with this. Who is allowed to run the old operating systems? Can I run them on behalf of thousands of people who are getting access in the cloud? I mean, you can think of all kinds of scenarios here. Can I get access to the source code if they no longer support the software? And the answer is maybe. So there's a lot of work to be done in order to create a digital preservation regime. Some of us, just a couple of weeks ago, Tim Berners-Lee and Brewster Kahle and I and others, got together to talk about the World Wide Web, because it has a problem too. The World Wide Web is today's web. It's not yesterday's web. And when you pull up an old web page with hyperlinks in it, and you click on them, and you get back, page not found, 404 error, because the URL didn't resolve, because somebody didn't renew their subscription to the domain name that was associated with the URL. And if you were using that, if you were relying on that resolving for something, you had no control over this. You know, he was the one that registered the URL, and he decided, I don't need this domain name anymore, and it ruins all of your references. So we're looking now at how we could build a self-archiving World Wide Web. So whenever you create a web page, things happen to make sure the hyperlinks are permanent and not ephemeral. And you can see all kinds of challenges here. But if we don't do this, we are going to be the invisible century, because the people in the 22nd century, when they wonder about us, won't be able to read our email, won't be able to see our blogs, won't be able to look at our web pages, because none of the software will work. And so we will be just this big black spot in history. And the pictures that you talked about of your grandfather and your great-grandfather, which have lasted 150 years because they're, the material lasts that long. None of our digital materials have ever lasted that long because they haven't existed that long. So we have a big challenge.
I think here, LaSalle could have an idea of something to do, which is a really important problem, huge problem worldwide, that Vint is showing to us. We experiment already that, no? But in this case, it's something that we could think about it. Let's move to the future now. That's the difficult part, because it's always easier to predict the past than to predict the future. That's why I focus on history. It's not But if we talk about the pros and cons about the Internet of Things, because not everything is nice, not everything is reduction of cost. There is a lot of energy to power all these devices, and we keep insisting of doing AC when most of the things go DC.
Yeah.
And then we, even in solar, in photovoltaic, it gives you DC, but then you switch to AC and then DC again, which is absurd, right? Maybe we should put a DC plug in the houses also.
Yes. Well, this is a good example of thinking a little bit about what we're depending on. So many of our devices run on DC power. We should wire the houses for DC and then get rid of all of those converters going from AC to DC. Mm-hmm. If you think a little bit about what it must be like or must have been like, before we had computers at home, we didn't exactly have a place to put them. And so as people started to acquire this equipment at home, you started to see homes being outfitted with a little place where you can put your computer and plug in the printer and stick the Wi-Fi. And so we've had to adapt our homes and our offices to deal with these new technologies. So this kind of DC power around the house is just another example of adaptation. It won't be surprising to me if that's the normal way you build a house in the future.
One idea that now let's be dynamic and think, if for a while you imagine that this year 2016 you get the job of Josep Martí Santos here, and you are the Director General of LaSalle, and you have to foresee the next, I'm not saying 40 years, but let's say 5-10 years, which is it's more reasonable. What would you do in his fit if you were because here we can change the studies, the plans, what are if you have to teach so many people, so many engineers, where would you lead them to?
So first of all, we have to think a little bit about the purpose of the university. And historically, it was the case that you got an education, then you got a job, and you worked for a while, and then you retired, and then you die. Well, it looks, first of all, like people are living longer. Second, their careers last longer. Their working lives last longer. And the jobs that are needed are changing over that period of time. And so the idea that you can learn everything you need to know in this one, continuous period, and then work, is starting to disintegrate. Mm-hmm. And in its place is coming the requirement to keep learning all during your career. Our schools are not organized around that very well. You don't want to stop your job at 20 years into the job and say, oh, I have to go back to school for 4 years. The economics of that don't look very attractive. You have, a wife and a dog and a car and 3 kids or something. So we have to start rethinking what it means to provide education. We have to think about what the working environment will be like. I still don't have a very good handle on how quickly jobs change. But if we look back into the past, think about the first industrial revolution and how we applied machines to jobs that people used to do by hand. And so you can start thinking now about what's going on with advanced manufacturing, with 3D printing, which completely inverts the way in which things get built. Instead of assembling something and then sending it to the consumer, you send the design to the consumer and the consumer produces it. Of course, the raw materials for that have to get to the consumer. So now you've completely switched the supply chain and the economics of manufacturing. So if it were my task, I would start out by trying to ask myself, how can I future-proof my educational system, taking into account that I'm going to have people coming back to me for new education and new learning over the course of their lifetimes. The second thing is that we know people learn better by doing something than they learn by somebody telling them about something. It's a lot more productive to do science than it is to listen to somebody talk to you about it. So we now have to think about the way in which we impart education. You remember the guilds, where we had you would come in as an apprentice, and then you learned for a while, and you became a journeyman, and you learned some more, and you became a master. That's not a bad way of learning. And we're starting to see some examples of that, where people are in school, but they are working also at the same time, learning to apply what they learned in the school.
The makers movement
Yeah,
also.
the makers movement is an example of kids learning a lot from actually making something. And it's a wonderful feedback loop, too, because the kids actually get excited about the thing that they made. It's not just a piece of software. It's something you can hold in your hand and say, I made that, and this is what it does. So this notion of changing the way we deliver education, I think, and also recognizing that it spreads over a much broader range of ages, I think is forced on us. This gets into another idea that we're trying out at Google, and I think you're trying out here as well, and that's where you bring young people together with the people who help make businesses happen. Business is not just about product. Business is about finance. It's about venture capital. It's about taking risk. It's about willingness to fail. It's about marketing and sales as well as engineering. And so we need all of those disciplines in order to create businesses. So if you're interested in turning out entrepreneurs, then you need to make sure that you have all of those disciplines available. Because the entrepreneur may have the idea about a product or a service, but maybe doesn't know how to do all of the parts of the company that are needed. So at Google in the UK, we put a building together that we called Campus. And the campus has 4 floors full of entrepreneurs who are all interacting, and a whole floor full of Google people who will help the entrepreneurs when they have questions and issues about what to do. And the whole idea here is to help people get through the cycle of invention, creation, and business development. Now, everyone sitting in this room, I'm sure, knows that startups don't always succeed. And in the Silicon Valley, we're lucky if 10 out of 100 companies succeed. And in fact, we sort of pray that 10 might succeed. If we're lucky, maybe only 3. So you hope that there will be 3 really big successes to make up for a whole lot of failures. But at least in the Valley, and I think generally true in the US, if you have a business failure, you don't end up with a permanent mark on your forehead. We accept the idea that a failure might be because you were stupid, it might be because you had a bad business model, and it might be because the market moved out from under you and your product is of no interest. That's not necessarily all your fault. And so if I were in the venture capital business and I had 2 people waiting here to be chosen for the CEO of the new company, and you had a business failure and you didn't have one,
I would pick the guy that had a business failure because he might recognize the symptoms before you would, because you never had that experience. Now, on the other hand, if you fail all the time, I'm picking the other guy. So we're not saying, failure is wonderful. But at Google, I can tell you, they tell us, take risk. We have these moonshots like the self-driving cars. The whole point is that aim high, because if it works, it's great. If it doesn't work, you learn something. If you don't learn anything, then this is not a good scenario. It's not a good recipe. But if you learn from failure, and you don't keep failing doing the same thing over and over, which is Einstein's definition of insanity, is doing the same thing over and over, expecting a different result. So this idea of assembling lots of talent and providing the resources needed to get companies off the ground is a powerful tool. It's a change in a way from what universities have been in the past. Because they mostly have been, we will teach you, and it's your job to figure out how to make your career happen. Now we're saying, wait a minute, we're going to not just teach you, we're going to enable you to learn how to make a business work. And so I think that if you had any option to allow this opportunity of business people and entrepreneurs and technologists to mix together, that's a wonderful recipe, even if we know that many of the things won't necessarily work. Mm-hmm. So but we have to get past this business about failure being, a mark of personal failure as opposed to simply a business problem. One other anecdote. There's a guy in Israel who started a company called Waze. Mm-hmm. And maybe some of you are using that or Google Maps. When he was talking to some young entrepreneurs, hopeful entrepreneurs in Eilat in Israel, he stood up on the podium like that one over there, and he said, I started 4 companies before Waze, and they all failed. But it wasn't fatal. I'm still here. And we bought Waze for $1.5 billion. So not too bad. That worked out pretty well for him. But he had to go through those 4 other companies to learn what to do. So I think that's part of the recipe. It's not the whole recipe. It's part of the recipe for changing what a university is capable of doing, and in some way directly contributing to the growth of the economy. And I think here in this country especially, we should be very conscious of the need to grow the economy.
Mm-hmm. Really true. So we will start to wrap up the conversation. We have to talk about sensorics, communications, big data. What do you think would be the key technologies in the future? It's not easy, this question, but some trends, I would say.
Well, we can certainly see some technologies which have actually come to significant fruition. I don't know how many of you have followed artificial intelligence over the years. It's been amusing, to say the least. 50 years ago, the definition of artificial intelligence was roughly, if it works, it's engineering. If it doesn't work, it's artificial intelligence. And I remember, I was at Stanford as an undergraduate, and we were trying to do translation. And so we got a dictionary, Russian-English dictionary. And we put the dictionary in the computer, and we said, okay, this is simple. Then we put in a sentence in English. We translated it into Russian. Then we translated back into English. So the sentence we put in was a very famous aphorism in English: out of sight, out of mind. So we translate it back, and it comes back, invisible idiot. Okay, so now we know there's more to translation than just putting the dictionary into the computer. Today, you're using, if you use Google Translate, you're using a very high order of artificial intelligence. It's using statistical measures for saying this phrase in this language is likely that phrase in that language. It's using syntax, it's using semantics. we have a semantic web. I shouldn't use that word because that's what Tim Berners-Lee means something special for, but we have a knowledge graph which is connecting 1 billion concepts to each other. There are 1 billion nodes in the knowledge graph. So what do you do with the knowledge graph? Well, the idea is when somebody types in search terms in the Google search, we apply those terms to the knowledge graph in order to see what other terms might be appropriate to expand the search for, to bring all the concepts back. And something else, I don't know if you do this here, but I noticed in the last 6 months, maybe year, that when I'm using the Google search application, I'm typing a whole sentence in with a question, because this is what I'm trying to find out, who invented, the dental floss. So I've been typing sentences and it works better. So I asked the guys who do the search engine, why is it working better? And they said, well, we decided that we would actually read the sentence, try to get the meaning of the sentence out by using grammar, by using the knowledge graph. And so if you really type in a question instead of just the search terms, you may actually get better answers from the system. So whenever you're doing search and translate, you're using artificial intelligence. When you talk to the mobile, whether you're using Siri or you're using the Google voice input, you're exercising artificial intelligence. And now some of you know the recent excitement from the Go game that Google's AlphaGo played. It was a very interesting experience. The AlphaGo team built a neural network, which is a piece of the technology of the future, that was several layers deep. Some of the older neural networks were just 1 layer deep. It's very simple kinds of adjusting of parameters in order to get the neural net to respond. But with multiple layers, it was absolutely incredible. So they played the games. They won 4 out of the 5 games. And at one point in the first game, I don't play Go, so I don't know what I'm saying here, but the move number 37 apparently shocked everyone who knew anything about Go. They went around saying, how could it do that? It was a move they'd never seen before. And it turned out to be a pivotal move in the game of Go. The computer had played millions of games with itself. They had the 2 neural networks playing back and forth with each other. They had them playing with other international Go masters. And it figured out a move based on its experience that no human had done before. Now, just to show you how dangerous it is to generalize from this, some of you will remember that there was a chess game played with Garry Kasparov in 1997 against the IBM Deep Blue. And in one of the games, the Deep Blue made a move that Kasparov could not understand. It made absolutely no sense to him whatsoever. But apparently he assumed that this machine, which was working, 200 moves ahead, must have some brilliant strategy in mind, and it really rattled his game, and he lost. Later on, we found out it was a bug in the program, and it was a stupid move. So we need to be careful about, patting artificial intelligence on the back. But that's one element for sure. The second one is the neural network technology in general. That stuff is moving ahead very, very rapidly. We are letting machines learn by doing things and feeding back to them, yes, this is good, or no, that's bad. In the end, though, we don't always understand why it worked. And so that worries me a little bit about inventing something that you don't know how it works. But that's one thing. Bioelectronics is another really important technology. We're at the point now where you're monitoring yourself. My wife has 2 cochlear implants. I don't know if you're familiar with these, but she lost her hearing when she was 3 years old. 50 years later, in 1996, she got her first cochlear implant. Electrodes are put inside the cochlea to touch the auditory nerve, and a speech processor, about the size of a mobile, computes the signals that are going to be used to electrically stimulate the auditory nerve. So sound comes in, the speech processor analyzes the sound, does a fast Fourier transform to see what frequencies are present and at what amplitudes, decides which of the, in her case, 16 electrodes to stimulate electrically in the auditory nerve. The brain interprets this as sound. We understand our sensory system well enough then, 20 years ago, to fake the brain into thinking it can hear by using this computer. And after she had the implant turned on, 20 minutes after they turned it on, she picked up the phone and called me, and we talked to each other on the phone for the first time after 30 years of marriage. I'd never done that before. It was amazing. Of course, by the time I got home, I discovered I had a 50-year-old teenager at home. I couldn't get her off the telephone. And then she, any solid marketing calls, hello, would you like to buy something? She would say, where are you? Oh, you're in India. Well, that's nice, how did you get there? And half an hour later, they'd say, are you going to buy anything? She said, no, thank you, but thank you for calling. Then she called the library, and she said, I want to get recorded books for the blind, because she wanted to hear words that she didn't hear before. She could read them, but she didn't know how they sounded. So remember, she's on the phone doing this with the library. And she says, oh, that's fine. Your name, address, phone number. Now, you're blind, aren't you? She says, no, I'm deaf. And on the other end, they're saying, how is that going to work? So she listened to 500 books on tape just, to hear words and understand what they sounded like. So the point I want to make is that in the ensuing period of 20 years or so, now we're starting to experiment with ocular implants. We're starting to experiment with implants that go into the spinal column to recover function of legs and arms that don't work. So the neural electronics of this 21st century are going to make a dramatic difference for lots and lots of people, including things like the heart things that we've had for years, like pacemakers and things like that, and defibrillators. So that's an area. Bioelectronics is going to be a big area in the future. And finally, I would say that our ability to understand our own biochemistry is also going to make a huge difference in the rest of this 21st century. Remember how excited we got when we finally got the first human DNA sequence? Mm-hmm. And we thought, wow, now we know everything there is to know about how our bodies work, and we'll figure out all the diseases that are caused by genetic problems. And then we discovered two things. The first thing we discovered is that depending on the methylation of the DNA, it gets interpreted differently. So now suddenly there are external effects that change the way the DNA actually is expressed. So now this is more complicated than we thought. This is theorem number 206, which reads everything is more complicated. So the closer you look, the more complicated it gets. So we have that problem. Then we discover one other thing. Sitting in the gut of the body are a bunch of bacteria. Mm-hmm. And they make up 100 times more DNA than our own DNA. But those bacteria co-evolved with us. And so they're a critical function of our immune system. They're a critical function of our ability to digest the food that we eat. They are fundamental to our existence as humans. So we're not just human beings. We're biological organisms that have this relationship with all the bacteria in our guts. And so it's going to be even more complicated to understand how our bodies are working. But we have now technologies that will let us sequence all of that, will let us understand a lot more about what's going on in the biochemistry of the body. So my prediction is that at least those three things will be major parts of our 21st century.
Great. And to wrap up, to finish the conversation, I would like to give the word to the floor, but take something in account, because don't make a speech. Please,
Yeah.
Please, just be synthetic, pose your question, so we can have more time for him to listen, and please, be very synthetic in your questions.
Of course, that's assuming that I have
Tindrem
anything
màxim
useful to say.
15
but that's
minuts,
okay. All right.
15 minuts per les preguntes. Aixequin, sisplau, la mà i els hi passaran el micròfon.
over there. Yes.
Hi. If when you were creating the internet, you had been in the same conditions where the startup system is today, meaning that we demand a big return on the 10%, would it have happened in this system, an innovation like the one that happened to create what we have today?
It would not have worked. Look, you remember I said to you from 1973 to 1983, we are working on the new protocols. Took us 5 years and 4 iterations. We had continuous support from the Defense Department before we got to the time we could turn the network on. And it continued to support the work for another, let's see, from 73 to 80 to 90, so another 17 years. The National Science Foundation starts its support in 1981, and it keeps going until it shuts down the NSFNet in 1995. So governments have the ability to take long-term risk if they're willing to do that. And this all comes down not to an institution, it comes down to individuals. We would call them program managers in the research agencies, being convinced that it's worth making the investment over a long period of time. I'll give you another example. You all heard in February about the announcement of gravity waves being detected. The Laser Interferometer Gravity Observer System, LIGO, had its origins in the 1960s. It sort of stumbled along for a little while, and then somewhere around 1976 or so, the National Science Foundation in the US made a $400 million commitment to a program of building and improving the laser interferometer gravity observers. And so they knew that it wasn't sensitive enough then in the 1976, but they had a program of improving. 40 years later, we see the gravity waves. And so it's only the government that has the capacity to do this kind of really long-term, high-risk, high-payoff research. And so the thing that I hope, I don't know enough about the Spanish government to know that this works.
There is no government.
Yeah, no. So the thing that we need, which even the US government doesn't necessarily do well, is not only patience and persistence for some of this long-term research, but also to push far enough along that enough risk is taken out that the venture guy is willing to take the rest of the risk. And in my case, in the case of internet, we had enormous long-term support. The first commercial activity on the internet was not commercial service, it was equipment, routers, that came around 1994. So we're talking about 10 or 11 years from the beginning. And it was very interesting. The client base for the routers were the universities. And the reason that universities were buying routers is because before the routers were available, the way you built a router was to take a computer and a graduate student, and you wrap the graduate student around the computer, and it turns it into a router. But they ran out of graduate students. So buying the routers was a business that Cisco and some of the other companies started. Only a few years later do we start seeing commercial service on the internet, 1989. So long-term investment, high payoff research requires patience and a willingness to support well beyond what the companies in the startup sector are willing to do. This, by the way, this is a problem for established companies too. I mean, we have this problem at Google. We're now a big company. We used to be 2 people. And now we're 62,500 people. And, you know, with all the structure that goes with that. And so inside the company, we're still trying to make ourselves entrepreneurial by allowing people to go try things out. So we have this 20% rule. You know how engineers are. They never do 100% on one thing. 20% of their time is on stuff that they're just curious about. So we said, fine,
Things
let's
that matter.
build it into the model. So we said, we'll organize the company around the assumption that the engineers will spend 20% of their time just exploring ideas. And we said, just don't do anything illegal, but otherwise, you're free to explore. So we've tried to keep this entrepreneurial attitude inside the company instead of having people leave the company to go start new businesses. So I'm sure that they're hiding in there. There is a sort of a formula that we could be thinking about, but it requires the companies and the government to recognize the importance of supporting this kind of risk, this exploratory risk. Okay, other questions?
The next question, please.
Yes, you were answering my first question about how Google is doing innovation. The second one is about entrepreneurs. We have here a lot of entrepreneurs at La Salle creating new things. What do you can tell them about the new startups that they are creating right now?
So, well, first of all, I have not ever personally started a company, so I might be a terrible source of advice. I've sat on boards of startups, and so I've been able to watch when things don't work and when they do work. So the first advice I would have for anyone who wants to be a CEO is it's a hard job. It's a really hard job. You have to be prepared to do everything in the company when you're first getting started. The most important thing that I learned from my internet experience is that it's not enough to be a technologist. If you want to do something big, you have to learn how to sell. And I don't mean selling products, I mean selling ideas. The only way you get anything big to happen is to get a lot of other people wanting to do the thing you want to get done. This is like the Tom Sawyer story where he's whitewashing the fence and he's convincing people that it's fun and you should come and do that too, and here's an apple core. So he was a pretty good salesman. So I try to explain to my engineers who say, oh, sales, it's kind of a silly thing. I said, let me tell you something. If this salesman doesn't succeed, you don't get paid. So this gets their attention. The other thing that I learned in terms of sort of entrepreneurial startup is the difference between marketing and sales. As an engineer, I thought, oh, it's sort of all the same thing, until I met the vice president of marketing at Xerox. And I said, what's the difference between marketing and sales? And he said, let me explain. The job of the marketing guy is to explain to the sales guy where to go and what to say when he gets there. That's the job of the marketing guy. Where is the market and what is it that you can say to them to get them to buy your product or service? So as CEO, has to appreciate all of that, has to understand, by the way, the difference between revenue and capital. When we had the big dot bust in April of 2000 in the US, it's because a lot of CEOs did not understand the difference between revenue and capital. Revenue is supposed to keep coming. Capital is finite. When you run out of capital, you are out of capital. You hope you don't run out of revenue. But if you don't understand the difference, you end up driving all the money away, throwing all the money away, and then you wonder what happened. That's what happened to 90% of the businesses that failed during the dot bust. Okay, so that's sort of how I would react to this.
La següent qüestió, sisplau.
First of all, thanks for all your work. I want to ask you about net neutrality and
Yes.
what will it happen with it?
Okay, so first of all, this term net neutrality gets interpreted differently depending on where you are in the world. And so I can tell you my interpretation of our experience in the United States. What I don't know is if it applies here, but I say what happened. In the US, before we had broadband service, there were 8,000 internet service providers. And the way you got to them was to dial up on the telephone with your acoustic coupler or the modem that sounded like two cats having their tails twisted. Yeah, right. So I never was able to really do that. So along comes the broadband technology. Everybody's excited. We can do things at many megabits per second. But it required a piece of equipment in your house. And so who could supply this equipment and the infrastructure to go with it? Well, the telephone company could do it with maybe fiber, if you were lucky, or DSL or something like that, or the cable company could do something. But it required you to have somebody come out to the house and install a piece of equipment. When we were in the dial-up regime, if you wanted to change the internet service provider, you dial a different number. Very low barrier. In the broadband space, you want to change broadband carriers. First, do you have much choice? Well, if you're lucky, maybe you have two. In most of the US, in the rural parts of the country, 0. If you're in the suburbs, 1. If you're in the urban part, 2, maybe. So you didn't have a lot of choice, and there was a big barrier to change. So this is not a highly competitive market. Now, those of you who know economics will know that if you don't have enough competition, that you get some very bad behaviors from companies that know that you have no place else to go. And so looking at the US, in the broadband market, we didn't see very much competition at all. Unfortunately, for many years, let me do this in two parts. The Federal Communications Commission, for many, many years, was told by the Congress, don't regulate the internet, leave it alone, we don't know what's going to happen. This is good advice, because it let us explore all kinds of possibilities. Then along comes the broadband, and the telco companies were regulated under Title II of our Telecommunications Act. And the cable companies were regulated under Title VI of the Telecom Act. So they're regulated differently. And that was okay for a while because one of them was doing telephone calls and the other one was doing television. Then they both started doing internet. And then they complained. They came to the FCC and they said, these two kinds of companies are offering the same service, internet, but we're regulated differently. This is not fair. So the FCC, I'm sorry to say, decided, well, the way we will solve this is we won't regulate anything. We'll make it an information service, a big, just uniform information service with no regulation. Well, the problem with that is that it ignored the fact that there really is a telecommunications layer in the internet architecture. It's built into the design. There's a telecom layer. It moves the packets. So they said, well, we'll just ignore that. So what we got was not enough competition and some bad behavior. For example, you're a company that offers broadband service. I'm the consumer. He's the bad company. You're offering broadband service and you offer video service and telephone service and everything. Okay, fine. So I buy your service. And then you start a company that's delivering video through the internet. So it's going this way. And I'm happy with that, but he's not. He says, wait a minute, you're taking away business from him. And so you get smart and you say, I see what's happening. This bad customer is buying video service from you. So I'll fix it so that your video service gets messed up on the broadband channel while the video service is working okay. And nobody will notice, right? Wrong. People did notice, especially the engineers. And they're saying, wait a minute. So we got worried that there wasn't enough competition to let the customer choose somebody else. And so now they're stuck. So the only solution to that is regulation. So the FCC more recently declared network neutrality rules that said you can't take advantage of the broadband control to do anti-competitive things. And so the FCC told some of the companies you can't do that. And the companies said, yes, we can, and they sued the FCC. And the FCC lost. And the reason it lost is because they had declared that the internet was not a telecom service. It was just this one information service. They had no basis for telling the telecom company or the cable company, you can't do that. So they declared that internet was a telecom service or contained a telecom service. They switched it back to Title II. Then they said, okay, there are lots of things in the regulation under Title II that don't apply to the internet. We won't apply those. This is called forbearing to apply. So they said, we will only worry about making sure you don't do anti-competitive things. They didn't say every packet has to be treated the same way. That's not what they said. They understand that some services need low latency and some don't. So the people who say you're making us treat every packet the same are actually wrong. It's smoke and mirrors argument. They would say, well, you won't let us charge more for more usage. And say, no, we didn't say that. You're free to do that. So there are a very small set of rules that they apply as net neutrality. And more recently, again, another suit came along saying, you can't do that. And the FCC said, yes, we can. And on the basis that it is now a Title II telecom service, they won. So now the FCC has jurisdiction to protect the customers from bad behavior from the companies that have market power or have control over broadband. And that's the story in the United States. I don't know how long it will stay that way, but I think it's the right outcome from my point of view. The best outcome, I shouldn't say it's the right, it's the best outcome that we could get under the circumstances. The better outcome would be to write a title in the Telecom Act for internet. And to say, if you're going to offer internet service, then you have to follow these rules to protect the consumers. But it's hard to get our Congress to do anything, especially right now, when some of us are thinking of migrating away from the United States, depending on who wins the election. So at this point, the best that we could do was to reassign internet as a telecom service and then regulate it in this limited way. So that's the story of net neutrality, at least in the US.
Bé, sembla que no ens queda gaire temps. Fem l'última pregunta.
This is going to be the last question.
Yeah, okay.
Hi.
Why is it that this side of the room got all the questions? I mean, there's something wrong with the people
No,
over
because
here?
she's with the microphone over there.
Yeah, well, yes, that
She's
helps. Okay, go for it.
Yes, automotive industry. So how you foresee in the future? Autonomous driving, vehicle to vehicle, vehicle to X.
I'm sorry, I didn't hear the question.
Automotive industry, how it will change in the future?
The cars.
The
car
self-driving,
industry,
yes.
how-
Okay, this is fascinating. First of all, don't hold your breath. Personally, I think we're a ways away from having self-driving cars that you can rely upon under all weather conditions. In good weather, our cars at Google do really well. I mean, they do. We've had a few little incidents, mostly caused by human beings who run into our cars. Although we did have one rather funny incident, two actually. One of them, the car came up to a street that was barricaded. And so the car program thought, well, if I just kind of squeeze around here to the left, the big bus that's over there will get out of the way. Except it didn't. So we ran into the bus. We ran into the bus at 3 miles an hour or something like that. So we had to reprogram everything to say, the buses don't always get out of the way. But in the funnier situation, we tracked the cars to understand the conditions that they encounter. And at one point, I wasn't there. I wish I had been, but I'm told that they were watching, and the car came to an intersection, and it stopped. And it didn't go anywhere. It just sat there. And so after a while, people were saying, I wonder what the problem is. So they turned on the video feed to see what was happening. There was a woman in a wheelchair with a broom chasing a duck in the middle of the intersection. And the car's program didn't have anything that said, if you see a woman chasing a duck while she's in a wheelchair, you're supposed to go this way. And so it just sat there. And of course, I wouldn't know what to do either. I was sitting, so I'd just be sitting there watching this woman chasing a duck. So when the cars are in good weather, they can see the street markings, They know where are the street lights, the traffic signals. They have really, really good maps. I mean, we get extremely high resolution maps. The GPS service is actually about a meter off. And so you can't just use GPS to know that you're in the correct lane. And you certainly have to use sensors in order to see people in cars and so on. The cars learn from each other, which is really quite fascinating. I always thought of them as being completely autonomous, but in fact, the cars are sharing their experiences. So, for example, when a car comes up to an intersection that it never was before, but other cars have been there, it has access to the information from the other cars. So, for example, if there's a tree, then it can check to find out, was there a tree there before? And so it knows that it's not supposed to wait for the tree to cross the road because it's not going to do that. On the other hand, if there's a person who comes out from behind the tree, it's supposed to notice there's something moving and don't run into it. So this is a cooperative environment. It's going to get more interesting as the cars begin to communicate with each other. And so we're exploring that, and others are doing the same. So you can imagine the cars are saying, I need to change the lane now, and all the cars in the area know that, and they can adjust for that, and then agree that you should go ahead. It's like when the cars come up to an intersection, there's a little protocol for figuring out who goes next. Now, when it's human beings, that protocol doesn't always work, especially if it's some, young kid, I don't care who got there first, I'm going through the intersection, my turn. So I think that eventually what may happen is that we'll have self-driving cars. They're driving on roads that are exclusively for self-driving cars, no humans allowed, because it's a lot easier for the self-driving cars to communicate with each other and to negotiate than it is to cope with human beings who are so unpredictable. So that's my prediction. But it's still a long ways from dealing with rain and snow, where the street markings are obscured, and you have trouble with the radar and other kinds of things. Mm-hmm. So I'm not holding my breath on the self-driving cars, but I expect to see them in special conditions, like streets that are restricted to self-driving cars, or maybe cars that go from depot to depot, as opposed to door to door. So we'll see. I mean, Elon Musk is more optimistic, I think, about self-driving cars. My wife has a Tesla, so we had some experience with this. And it's actually a pretty interesting thing. It will park itself in the garage, for example. You just tell it, go to your room, and it goes to parks in the garage. I was really scared the first time we did that because I have a 98 Jaguar over next to this, and I thought, please don't scrape the car. But turning it loose on its own, not yet. So, don't hold your breath.
Okay, thank you. So let's wrap up. Acabarem aquí la conversa. We should make a little executive summary. We have been talking about the internet, about the past, the hidden history of this NSNet with the mother of the internet. Come back home thinking that the ARPANET is not the mother of the internet. Probably the NSNet, yes. And also then we have been talking about problems that this digital world is coming with the pictures, photographies that probably our sons won't see because we don't have much care of where we put these pictures or how we sort it in order to retrieve later on. We have been talking about the future, about what LaSalle could do in many aspects. Probably in this, when he was talking about creating a center where you can emulate different operating systems and different legacy, that you could have a PowerPoint, for following your example, a PowerPoint from 1997 that you could, of course, open. And then also, talking about the trends that the technology will bring. And finally, talking a little bit that the future, I think we could wrap up, is saying the internet will be faster, cheaper, and smaller. And we don't move on that, right? What do you think? Is that
well, and also be more ubiquitous, and there will be more access to it. I got told by the chairman of Google that I wasn't allowed to retire. And I said, why not? And he said, well, you're only half done. You only have 3.5 billion people online. You have another 3.5 billion people to go. So I can use some help.
Okay, thanks for coming. It's a pleasure to interview you and to be here. And gràcies, moltes gràcies per estar amb nosaltres i espero que hagueu disfrutat tant com jo he disfrutat d'aquesta conversa amb el doctor Vint Cerf.
Thank you, Andreu.
Thanks so much.